Okay, so today it's going to be another introduction to analog IC design. And this course or lecture is not for analog designers. This is for the people that don't do analog design every day, to try to inform you about what the design community does. So I'll try to summarize different topics. The two main topics I'm going to talk about today are current and voltage generators, and then switches and MOSFETs. Okay, so at first glance, analog circuits can be confusing and difficult to follow. However, most analog circuits are designed using a common set of building blocks. And in this talk, I intend to introduce you to more of these building blocks. I started last week with some current mirrors. In addition, I'm going to attempt to familiarize you with many of the common terms used by analog designers. And some of you might be surprised, many of those terms have more than 4 letters. Especially if you're up on our hallway during takeout time. Okay, so most analog ICs use currents to bias the transistors, aka the active circuitry, in a known DC operating state. And so here's this active circuitry. Here's an example of what a reference current generator or DC bias circuit might look like here. This current is being mirrored up here and over and down and providing DC bias currents for this active circuitry. So in the first part of the talk here, I want to show you different ways of building this reference current generator. However, by the way, I wanted just to make notice these transistors here. We talked about this last month. These are what's called diode-connected MOS devices. And if you hear designers talk about diode-connected devices, it's basically just a MOS device with its gate tied to its drain. And these tend to act as the reference voltages for the current mirrors. So this one would be the reference voltage for this upper current mirror. This one would be the reference voltage for the lower current mirror. Okay, before I get into how to generate these currents, I just wanted to mention that bipolar transistors can also be used as current mirrors for distributing the bias currents to the active circuitry. And the example here, all I did was I replaced the MOS transistors with their corresponding bipolar transistors. However, unlike MOS transistors, bipolars draw base current, and those base currents can cause inaccuracies. For example, all these base currents on this line would be coming out this node down into the IREF and messing with the value of the IREF current. All the base currents on this node would be messing with current on this leg here. This is especially true at low temperatures where the beta, which is the current gain of a bipolar, the collector current over base current, drops off. So all these base currents go up at cold temperature. Cold temp's usually the worst case for this particular problem. When you're using bipolar current mirrors, it's common to add other transistors to help reduce the base current error. And these transistors are known as beta helpers. And I just showed 2 of them here, this P2 and N2 here. I've added those in here, and you can see what they do is they take all that base current, and instead of shunting it, in this case to the reference current, we're shunting it down to ground, or we're pulling it off the supply. This reduces the current error by a factor of beta squared, instead of just a factor of beta. The disadvantage of these beta helpers is they add an extra VBE. If you're going to use these with very low power supply requirements, you might have a problem. Most of the time you'll be able to use these, but I just wanted to mention what they're called and how they're used. Okay, so now let's talk about current generators. So how are these currents generated? So one simple way would just be use a resistor to generate a reference current. And you can kind of see, if this was the case here, you'd be starting up at VDD, dropping a VGS on this device, and that voltage would be across the resistor. So the current through the resistor would just be VDS minus a VGS over R1. And then that current could be mirrored all over the place if you wanted it to. The main problem with this type of arrangement is it's going to track VDD. As VDD goes up and down, this current is going to change. And you really don't want that in a current reference circuit. You'd like your current reference to be independent of what the supply voltage is. That's often called power supply rejection, or PSRR for power supply rejection ratio. You'd like a good power supply rejection ratio. Now, in addition, resistors are going to have volt codes and temp codes, and you have to deal with those. But all these current generation schemes have resistors in them that you have to deal with volt codes and temp codes. The main disadvantage of this is power supply rejection. So then here's a different way to generate currents. This is using a Zener-based approach. And the way this works is we have this resistor R2 and we trickle a little bit of current into this Zener diode. So this Zener diode turns on and establishes a voltage right at the top of the Zener, right where I'm pointing. And that provides some gate voltage for this transistor right here, turns it on, and provides a voltage right on top of resistor R1, which is basically the Zener voltage minus a VGS over R1. So that's going to establish a current down here. And then you mirror that current around, and that goes out all over the chip. Now, this is fairly independent of supply. You can move VDD all over the place, and this Zener voltage doesn't move much. The disadvantage of this scheme is Zener diodes, about the lowest you're going to get is maybe a 5-volt Zener. It's typically 5 to 7 volts. So if you're trying to operate at a 3-volt supply, a 5-volt supply, it's going to be trouble. You're not going to be able to use a Zener approach to generate your currents. So now I want to talk about a PTAT current generator. And this is a more advanced configuration that takes advantage of match devices to generate a reference current. And I'll talk about that term PTAT in a minute. Note the ratio between P1 and P2 and N1 and N2. P1 and P2, this 1-to-1 means they're matched. They're the same size as each other. N1 to N2 means there's a ratio of 1 to 8 here. So this transistor right here is going to have 8 times the emitter area as N1. If we assume that the base currents are really small, the current in this branch and the current in this branch are going to equal each other because these transistors up on top are matched. So they're saying this current has to equal that current. Now, if we look down here at this loop, you can see that the base emitter diode of N1 is in parallel with the base emitter diode of N2 and R1. The VBE drops on these diodes aren't going to be the same because this diode is a lot bigger, 8 times the size. So it's going to have a lower voltage on it. So that's what we're seeing in this equation here. We're saying the VBE of N1, that's this guy, is equal to the VBE of N2 plus R1. And what we're doing is we're looking at this loop right around here that I show in red. So if we rearrange this equation and we solve it for the current, we come up with the current is the difference of 2 VBEs divided by this resistor. I'm not going to solve this equation. It's solved for you in Appendix 1 if you really want to go see the math. For now, you're just going to have to take my word for it with my hand waving that the solution comes out to KT over Q times the log of 8 over R1. That's going to be, this current right here, which is the same as this current, which is the same as your output current as long as all your transistors up here match. Again, I'm skipping the math, but if you really want to see it, I know Michael might want to see it. It's in Appendix 1. You can go look at it. K is Boltzmann's constant. Q is the charge on an electron. T is the absolute temperature in degrees Kelvin. The log of 8 here is just the ratio of these 2 transistors. And then R1 is the resistor value. By the way, KT over Q is sometimes called VT, and that's the thermal voltage. So if you hear someone talk about VT or thermal voltage, that's this parameter KT over Q, and at room temperature, it's about 26 millivolts. So what does this equation tell us? Well, like I said, K and Q are both constants, and we can pick a value for R1, and we pick the value for the log of 8 just by ratioing these guys here. Using the R1 and the log of 8, we can set these currents to almost anything we want. Now the variable T, if you look at the equation up on top here, I pulled T out. So this is saying temperature times a whole bunch of other stuff. So this is telling you that this current is going to be proportional to absolute temperature. That's what PTAT stands for, proportional to absolute temperature. So if you hear about a designer talk about PTAT, that really just means it's something that increases as temperature goes up. So that's what these currents are going to do. They're going to increase with temperature. Now, of course, the resistors are going to have a temp code that is also going to come into play, and you have to deal with that. This circuit has pretty good power supply rejection. It's fairly independent of supply voltage. However, what do you do if you don't want a current that increases with temperature? What are your other options? Well, what if you want a current that decreases with temperature, aka a negative temp code? It just so happens the forward drop of a PN silicon diode has a negative temperature coefficient, and it's around 2.2 millivolts per degree C. So that means if you pumped a fixed current through a forward bias diode and measured the forward voltage drop versus temperature, you'd see about 2.2 millivolts less for every 1 degree C rise in temperature. And this graph over here demonstrates what that looks like. This is the forward part of the diode, the forward VI curve of a diode. At room temperature, you get about 0.7 volts as your forward voltage. We're all pretty familiar with that. But if you took that to cold temperature, oh, that voltage goes up to maybe 0.8 volts. If you took it to hot temperature, oh, that voltage goes down to maybe 0.6 volts. So the diode voltage is changing by about 2.2 millivolts per degree C, but in the negative direction. The diode voltage goes down as temperature goes up. So if we could somehow take that forward diode voltage and impart that voltage across a resistor, the resulting current would also have a negative temperature coefficient, just like the diode does. That's what the circuit on the right here does. You can see R2 here is pulling up on the gate of N1, turning it on. N1 turns on, we start pulling a little bit of current through here, and that turns bipolar device N2 on, which pulls down on the gate of N1. This circuit, due to this negative feedback, is going to settle just in the right spot where you have a diode drop across R2. So the VBE of N2 is going to be applied right across R2. And we said that any diode has a negative temperature coefficient. So the current through R1 here is going to also have a negative temperature coefficient because it's going to track the diode voltage. This is known as CTAT, or complementary to absolute temperature. And you'll often hear designers talk about CTAT, and all it means is a current or voltage that goes in the opposite direction to temperature. The voltage or current is going down, as temperature is going up. That's correct. You always have to take into account the temp code of the resistors. We have resistors with positive temp codes, with negative temp codes, and with near zero temp codes. And in fact, if you can mix and match positive temp codes and negative temp code resistors together to generate a zero temp code resistor if you really want one. But good question. Thanks, Dave. So what if you want a reference current that doesn't vary with temperature? So this type of reference current is known as ITAT. And ITAT means insensitive to absolute temperature. Now it's really difficult to generate an ITAT current directly. However, we can generate a PTAT current proportional to temperature, and we can generate a CTAT current that's inversely proportional to temperature. Well, if you sum those two together just right, you can get a summed current that's almost flat over temperature if these two cancel each other out. So here's a graph over here that shows how that kind of works. If you have a PTAT current, that means it's increasing with temperature, a CTAT that's decreasing, and if you come up with a circuit that adds those two together, well, you might be able to get a current that's fairly flat over temperature, and that would be ITAT, or insensitive to absolute temperature, at least to the first degree. These things are never perfect. So here's one way that might be accomplished, and here's the conceptual diagram. So what we're going to do is we're going to generate a PTAT current, We're going to generate a CTAT current. We're going to cram them into the summing node, go through a mirror, and that mirror sums them together and then generates an ITAT current coming out the other side. Over here, this would be one possible way this could be generated with actual transistors. Everything on the left here is to generate your PTAT current, and your output of the PTAT current would be coming right here. Everything in this middle section generates a CTAT current, and its output would be right here. Then we sum them at this node and run it up through a mirror and back down, and you get an ITAT current coming out. So this is just one example of how this might be done. Believe me, there are many, many ways of doing this, but I'm just trying to give you the idea of how you would generate these currents that are stable over temperature. So now I want to talk about startup circuits, and this is mainly for PTAT current generators. In Appendix 1, Michael's favorite, we solved simultaneous equations, and I know I didn't solve them, but if you look in Appendix 1, you'll see it, to determine that the output current is KT over Q times the log of 8 over R1. That's the equation. I'm hand waving. You just have to believe me that works. However, if you looked at the math, there's a second stable solution for those equations. And that second stable solution is if all the branch currents go to 0. And that's very bad. That means you turn the power on and the circuit just doesn't start up. You get nothing. And that's known as a startup problem. And believe me, it is very undesirable. This is the kind of thing you'll get calls in the middle of the night from your management about if something happens like this. So you want to avoid startup problems at all costs. Typically, just the leakage current is enough to kick these things on. All you need is a little bit of current to trickle through, and it'll kick it on, and it won't settle at the 0 current state. It'll settle at the other stable point that you want it to settle at. However, not always, and especially at cold temperature. The leakage currents can be very small at cold temperature. So these startup problems, you'll never get a startup problem at hot. It always happens in cold temperature. So to avoid the startup condition, we add special circuits to these current generators to prevent them from settling at the 0 current state. And one example of a startup circuit I'm showing in red over here, and I'm going to briefly explain how that works. If for some reason this PTAT generator over here didn't start up on its own, this startup circuit is designed to trickle a little bit of current in here and kickstart the thing on. And the path for the trickle current would be down through R2, through this forward bias diode, and then through another forward bias diode, which is the base emitter of N1. So it looks like a DC path right there. So there's no way you're going to stop that current from happening. It's going to happen because there's a DC path. So that's going to kick this thing on. So once this thing starts up, now you start pulling all the normal currents. Well, now N3 comes on, and N3 pulls node V3 down. So this diode that used to be forward bias, now becomes reverse bias. That reverse bias diode draws very little current and doesn't affect the normal operation of the generator. So really, essentially what you're doing is you're providing a DC path that ensures that the startup circuit or that the circuit's going to start up. However, once startup occurs, we're altering the path to avoid interfering with the normal operation of the circuit. That just gives you an idea of what these startup circuits do. There are lots and lots of ways to generate these startup circuits. Okay, I'm going to show you my favorite ITAT current generator. So if you ask 10 designers what's their favorite ITAT current generator, you'll probably get 10 different answers. So here's my favorite. R3 provides some DC current. So no additional startup circuit is needed. This thing's going to start up by itself all the time, guaranteed. And if we go around this figure 8 here and add up all the VBEs, what you can see is VBE of N4 plus VBE of N2 has to equal VBE of N1 plus VBE of N5 plus R1. That's this equation right here. However, if you neglect base currents, and you look at this branch right here, you say, oh, N1 and N4, they're in the same branch, so they have the same collector current. We're neglecting base currents, and they're matched, one-to-one devices. So this VBE and this VBE are going to match each other, going to be almost identical. So if they match, one of them's on one side of this equation, one of them's on the other side of the equation, well, we can just cancel those out since they match. Now we're down to the same equation that we've had many times before, where the current in this side over here is just the difference of two VBEs divided by R1. This is the same exact equation we solved for in Appendix 1. And it comes back to KT over Q times the log of 8 over R1. That's this current. And it's a PTAT current, so it goes up with temperature. So how about this current over here? Well, if we look at, let's count some diodes. We'll go up a diode here, we'll go up a diode here, then come down a diode here. So that leaves one diode voltage across R2. We went up 2 diode voltages and down 1. So the voltage across R2 is basically a diode voltage. And we said a diode will have a negative temperature coefficient. So the current through R2 is going to have a negative temperature coefficient. So that's going to be a CTAT current. So now we can add those two currents together through this current mirror and generate an ITAT current. And like I said, this is my favorite one. It's nice and compact. It works pretty well. By the way, you'd want to use matched resistors for R1 and R2. You'd need a ratio here, but you'd want to use a unit resistor, make them out of the same type of material, and all those matching techniques we talked about last month. So in addition to currents, sometimes integrated circuits are required to generate voltages. And those voltages, we want them to be stable over variations in temperature and supply voltage. So this class of circuits is widely known as bandgap reference voltage generators. And I'm going to show the simplest bandgap over here. If you look at this, everything to the left of the dashed line is that same PTAT current generator that we've been talking about all along. And all it does is generate a PTAT current. All we've done is we've taken that PTAT current and dumped it through a resistor and a diode. So the output voltage here is just going to be the drop of the diode plus the drop of the resistor. Let's talk about that. So we know from many, many times, the output current is going to be this KT over Q times the log of 8 over R1. And the drop in the resistor is just going to be that current times R2. So that's the left-hand part of this equation right here. The right-hand part of this equation is just the diode drop. So if you look at this, this one on the left is proportional to temperature. It has its T in here. R2 and R1, if they have any temp-co, they're going to cancel out because you make them out of the same type of resistor, same material. So this the left-hand term is going to be positive temp-co, and the right-hand term is going to have a negative temp-co. So if you ratio things just right, you can cancel out the negative temp-co of the diode with the positive temp-co of the resistor. And you can get a resulting voltage that's fairly flat over temperature. And that voltage is typically going to be about 1.2 volts. Now, here's an example of what a well-tuned bandgap voltage generator output might look like. This is, I simulated the cell bandgap generator here. And you can see it's pretty close. It's a little over 1.2 volts. And I'm sweeping it all the way from minus 55 all the way up to 150 degrees. And so it's a very wide temperature range here. And it's only changing by maybe 4 millivolts over this whole temperature range. So it's pretty flat. It looks pretty good. Sometimes you need better than that. And I'm not going to talk about how to do that, but I'm going to demonstrate what you would do if you needed more accuracy than, say, 4 millivolts over this full temperature range. And this is called curvature compensation. This is not simulated. I just drew this curve in here. But what curvature compensation does is it comes in here and it puts a kink in the curve. So instead of just curving in one direction or curving in the other direction, you get this little kink in the curve. And sometimes they put multiple, usually it's just one. But you can see by doing that, you'll get less variation over the full temperature range. That is a topic for another day. No, the magic voltage is usually the voltage that you're going to trim to make this thing flat. And that's usually somewhere around 1.2 volts. It might be, in this case, it's like 1.24 volts or something like that. But the magic voltage would be the voltage that you need to trim the band gap to get it to be as flat as possible. I should have shown all the different trims. You know, if you're off, this blue curve might tilt upward or tilt downward. You want it to be flat. So you trim to the magic voltage, which gives you the flattest over temperature response. No problem. So anyway, if you hear the term curvature compensation, you kind of get an idea of what it is. Most of our band gaps don't need this kind of accuracy, but sometimes you'll hear it or see that term. Okay, so let's talk about bandgap voltage generators. Here's a way to generate one using a bulk CMOS process. So all you have here is CMOS devices. You have a bunch of PMOS devices on top. You've built an op amp. The op amp is set up to change the current here, and due to negative feedback, voltage 1 and voltage 2 are going to be regulated to almost the same voltage within the offset voltage of the op amp. So if we go around this loop here, we say that this voltage at the top of P2 is the same as the voltage at the top of R2. Oh, we have that same exact equation again. The voltage across R2 is just a difference of 2 dBEs. So it's going to have that same solution as always. It generates a PTAT current. That PTAT current mirrored over to the left side here goes through a resistor and a diode, and we generate our 1.2 volt output just as we did in the last circuit. Now, one thing I wanted to mention, this is an all CMOS process. How do I get bipolars in an all CMOS process? Well, these are substrate PNPs, and I'll show you in a minute how to make a substrate PNP. Here's another bandgap voltage generator, and this is in a bulk CMOS process. Again, no bipolars in this process. But here, we're not going to use an op amp anymore. We're going to stick some transistors in here. And the trick here is, since we have a 1-to-1 ratio on top here, that says the current in this left branch and the current in this right branch have to equal each other. And since these two transistors are matched 1-to-1, and they have the same currents running through them, we're saying, oh, this VGS and this VGS are identical. If we went around this loop, those two VGSs are going to cancel each other out, and we end up with the same exact equation again. The voltage across R1 is just the difference of 2 VBEs here. And so once again, it generates a PTAT current. That PTAT current is mirrored up here and put through a resistor and then through another diode, in this case, a substrate PNP. So again, this is how you might generate a bandgap voltage if you were in an all CMOS process. Now, I'd like to show you what a substrate PNP is. So I just want to take this moment and explain it. So here's a cross-section of what a bulk CMOS process would look like. You know, you have your NMOS devices, you have your PMOS devices, and typically that's all you'd get. You'd get PMOS, NMOS, and a bunch of resistors. That's all you'd have here. However, you can construct a vertical PNP that I'm showing in this circle here, and it's made up from P plus, N well, and P substrate. The only thing here is the collector has to go to the substrate. It can't go anywhere else. And that's why it's referred to as a substrate PNP. But if you're doing a bandgap in all CMOS process, that's the device you're going to use. So here's an all bipolar bandgap. Now let's talk about how this works. So if we go around this loop right here, you can see that once again, the drop across this resistor is going to be the difference of 2 VBEs. So that generates a PTAT current. So this PTAT current here, and this 1-to-1 ratio up here forces the current on the left and the current on the right to be the same. And those two currents get added down here. They're both PTAT currents. So the drop across R2 is PTAT. That drop gets added to the VBE of N1 here. So this is your diode, that's your resistor, and that gives you your output voltage. This is a very common circuit to be used in an all bipolar process. If I was going to use this, I'd stick a startup circuit on it. This one doesn't have a startup circuit, but to make sure it starts up at cold temperature. Okay, so that pretty much does it for current and voltage generators. Now I want to talk about analog switches. At first glance, switches may seem relatively simple. I mean, the basic idea is to connect point A to B. So how hard can it be? However, analog switches can sometimes have spec requirements that can be challenging. So here's your basic NMOS switch. If we apply a high signal to the gate terminal, that'll turn the switch on and it'll connect A to B. If we apply a low signal to the gate terminal, it shuts off and isolates point A and B. But what would the on resistance of the switch look like if we tied the gate terminal to VDD and then swept the input from 0 up to VDD? At low VNs, the voltage on the gate to source, that's VGS of this device, is high, so the resistance will be low. As VN increases, the VGS voltage decreases, and the resistance curve looks similar to what I show here. So the resistance is going to go up as VN increases. Eventually, the device is going to shut off. It's not going to make it all the way up to VDD. And so it's going to shut off when you get within about a threshold of VDD. What if it was a PMOS device? The PMOS device looks very similar, it's just flipped. At low input voltages, you're going to have a high resistance, and then the resistance goes down as you go to higher input voltages. At extremely low input voltages, anything less than a threshold, the PMOS device is going to be off, so the resistance is going to look really high. So typically, neither the PMOS curve or the NMOS curve is very desirable for a switch because the on resistance is going to vary greatly with the input voltage. However, if we place an NMOS device in parallel with a PMOS device, the curve is fairly flat over a wide range of voltages. And you can see what we're doing here. We're putting a PMOS device in parallel with an NMOS device, and then looking at the resulting resistance curve. This is called a CMOS switch. And this is kind of what the curve looks like from a resistance standpoint. R on and R on flatness are both important switch specifications. R on is pretty much R max. The R on flatness curve is kind of an important specification for switches. Basically, R on, you have a maximum and you have a difference between R max and R min. This curve we show here is fairly ideal because the peaks are matched. Sometimes you'll see curves that look like this, where one of the peaks is higher than the other peak. And really what that means is that the two devices, the N and P devices, aren't ratioed in size correctly. Either one of them's too big or one of them's too small. Typically, you're going to want the PMOS device to be about 3x the size of the NMOS device to get this to look pretty flat. And again, I think we've talked about that before. It's mainly due to the electron versus hole mobility, why you'd have a 3-to-1 size difference in PMOS and NMOS. So the example shown here, we have the bodies of the switches tied to the appropriate supplies to keep all these drain to body and source to body diodes reverse bias. I just drew the diodes in here, but you know, they're in there all the time. You just don't normally draw them. The threshold voltages of MOS devices are affected by the voltages applied to their bodies. And the higher the reverse voltage across the source to body diode, the higher the threshold voltage of a transistor gets. This is known as the body effect. And higher thresholds are going to cause higher R-ons, which you don't really like, but higher thresholds also cause lower leakage current when the switch is off. So you kind of like that. And by the way, if you want to see the details of the body effect equation, I show that in Appendix 2. Michael can go look at that one. Okay, so designers will sometimes take advantage of this body effect to improve the performance of the switch. When the switch is off, you want high thresholds to minimize the leakage current. So this is what you want the switch to look like when it's off. You want the bodies to be tied to supplies. However, when the switch is on, you want low thresholds to try to get the lowest R on of these devices possible. So in that case, you'd like the bodies tied to the sources. So how are you going to do this? Well, one way to accomplish this is shown here. These are called body draggers. So if you hear designers talk about body dragging transistors, they're talking about transistors that are used to move the body of the switch depending on whether the switch is on or the switch is off. And we're trying to take advantage of the body effect to optimize the performance of the switch in either the on case or the off case. The way these work is we've added a bunch of transistors, P2 through P4 here. They control the body of the PMOS device here. And then we've added a couple of transistors down here, N2 through N4. They control the body of the NMOS device. When the control signal is pulled low, all the black transistors are turned off and the red transistors are turned on. Let's take a look at P4 here. P4 is pulling the body of all these devices up to VDD. So that gives you the maximum threshold on these transistors, which means their leakage current is going to be minimum. And that's what you want when the switch is off. Likewise, down here, this transistor N4 is on, and it's pulling the bodies of all these off transistors to ground, and that gives them the highest threshold. So that makes them have the lowest leakage current. This gives you the highest threshold and the lowest leakage current in the off state. What about the on state? So if you pulled your control pin high, now all the transistors in red turn on and all the transistors in black turn off. So let's just look at the PMOS device up here. If P2 and P3 are on, that takes the body of P1 and pretty much puts it in the middle of our A and B terminals. Well, if the switch P1 is on, the two sides of the switch are going to be almost at the same voltage. So really what we're doing is we're tying the body to the source. And that drives the threshold down as low as we can get it to get the R on as low as we can get this device. Similarly, on the NMOS device, it's done exactly the same way. When N3 and N2 come on, they drive this body here to the midpoint of terminal A and B, and that gives you the lowest threshold on this N device to drive its R on down. So once again, this is body draggers. If you hear that term, now you have an understanding of what it's used for and what they mean when they talk about it. Next, I'd like to talk about T-switches. Off isolation is sometimes an important parameter for switches. So one way to improve off isolation is to use a T-switch configuration, and I show that configuration right here. And the configuration uses two series switches, S1 and S2, to connect point A to point B. Then we have a third switch that connects the center node to ground. When S1 and S2 are closed, we want S3 to open, and that allows the switch to work normally. However, when S1 and S2 are open, as shown in this diagram, we want S3 to close, and that grounds this center point. And what that does is that this improves the off isolation. If you have some signal coming in on the A node and it's leaking through, say, switch 1, well, now you have this point, tied pretty hard to ground. That's going to make it hard for that signal to leak through to B. So this gives you a way of increasing the off isolation of a switch, if that's an important spec for you. When transitioning from the off state to the on state or vice versa, it's important that these individual switches be configured in what's called a break before make operation. And for example, if the T switch is on, S1 and S2 are on and S3 is off. So that's this configuration here. And if we're saying we're going to transition from the on state to the off state, so S1 and S2 are going to be opening and S3 is going to be closing. What you don't want to do is you don't want to have all three of these switches closed at the same time, because that's going to pull your inputs A and B to ground. And that could make the transition very messy, or a very undesirable transition from on to off or off to on. So what the break before make does is it makes sure that we open switches before we close the other switches. So we never have all three switches on at the same time. You've probably heard this term many times before. Next, I'd like to talk about audio switches. Analog switches are sometimes used to transmit audio signals to speakers or headphones. And audio switches typically have a left and a right channel for transmitting stereo. Since these switches may be driving low resistive loads, such as 8-ohm speakers, you want their R-on to be fairly low. The amount of signal loss across the switch is known as insertion loss. You may have heard that term before. And it's basically how much energy you're losing across a switch or a cable. And it's basically the difference of the incoming signal and the outgoing signal and in decibels. So you take the ratio of the signals and take 20 times the log of that. And that's insertion loss. And it's just a measure of how much power or energy you're losing in the switch. In addition to transmitting desired signals, switches can also transmit unwanted noise known as click and pop. And we're probably all familiar with the annoying sound some audio electronics makes when you first turn them on. You get this very rapid sounding pop in your ear. Typically, this noise is caused by a rapid discharge of capacitor into a load, as I showed this diagram over here. Especially if this capacitor gets pre-charged, that spike of current can be pretty hefty and flowing right into a speaker, and you're going to hear it. So many audio switches, they attempt to suppress this unwanted noise, and that's known as click and pop suppression. It's typically done by implementing another switch that works in conjunction with the switch that's transmitting the sound. So this switch is basically just a switch to ground. It's a shunt switch. And again, these two get arranged in a break before make operation. What you want to do is you want to ground or discharge any capacitance on this node using this switch and open this switch just before you close this switch to connect your source to your load. You don't want a long time delay in here, because you don't want to give this cap a lot of time to charge up before you close your switch to bring in the load. Anyway, this just shows you what click and pop suppression, if you've heard that term related to audio switches, that's what they're talking about. Total harmonic distortion, or THD, is also a major concern with audio switches. And if you're transmitting music, you don't want it to come out sounding distorted. However, if we use the standard CMOS switch topology we discussed earlier, that can sometimes cause distortion in audio switches, because the R-on, the on resistance, varies as you swing the input voltage up and down. What we show on the right here is a configuration that has superior total harmonic distortion over a very limited range of operating voltages. This configuration uses just an NMOS device. It's no CMOS switch. It doesn't use NMOS or PMOS, just an NMOS device. And you turn on the switch by controlling a current and a shunt NMOS device to ground. During the off state, you shut this current off and you turn the NMOS on. That pulls the gate of this NMOS switch to ground and shuts it off, just like before. Everything's off, no problem. But when you go to turn it on, now what you do is you turn the NMOS switch off. Now you pump a current in here. That current goes down through these diodes and exits out B. And it's a small current, so it doesn't really interfere very much with the B terminal. But what this does is it gives you a constant VGS, basically two diodes on this NMOS switch. And now if you have a signal coming in on A that rises up and down, this side is going to rise up and down with it because you're not tied hard to a supply anywhere. What this does is it gives you a region where R on is very flat because you're operating with an almost constant VGS in that region. So what we do is we restrict operation to just this flat region here, and you get a lot better total harmonic distortion. And let me explain why. So if you had a switch, as we show up on top here, where the resistance of the switch and the resistance of the load were all fixed, they didn't move at all, and you put some sine wave in here, you're going to get another sine wave out the right side here. And it might be lower in amplitude due to insertion loss, but since everything is linear, the spectral content of these sine waves are going to be the same. There's no distortion. However, if you have a switch where the R on changes depending on the amplitude of the signal coming in, that's going to add spectral content to your output here, and basically you come up with a distorted signal. So that's why use that other circuit that I showed you as an improvement for total harmonic distortion in audio switches. Okay, analog multiplex is my last topic for today. So an analog multiplexer or MUX is short for an arrangement of switches with multiple inputs and one output that allows you to select which input gets connected to the common output. And I show kind of a functional diagram, what that would look like over here. You'd say maybe have 4 inputs, and you have a wiper where you're just going to select which of those 4 inputs go to the output. On an IC, you'd probably have 4 switches and some type of decoder logic that would select which of these switches to turn on and which of these switches to keep off, allows us to operate properly. And these switches could be NMOS, PMOS, CMOS, whatever you want, depending on the specification. Here's an example of a different way to build an 8-to-1 MUX that doesn't require a decoder. It's kind of self-decoding. So in this case, what we've done is we've shown separate paths from each of the 8 inputs to the output. The binary combination of the 3 select bits pick which of these paths to energize. You can kind of look at the truth table to see the details here. If you wanted input number 4 here, well, we pick 1, 0, 0. So that would be 1, 0, 0, we'd get to input 4 here. And if you wanted input 1, you'd pick 0, 0, 1. That would be 0, 0, 1. So you can kind of see, this is just another example of how an analog MUX might operate. And this one doesn't need a decoder. I did want to mention there are differences between analog MUXes and digital MUXes. As I said, the analog MUX is basically a switch. And that switch can pass current, it can pass voltage, it can pass logic levels, just about anything you want. Digital MUXes, on the other hand, they only pass 1s and 0s. So I show a representation of how you might make a digital MUX down here. For example, if you use the select bits to pick channel 0, whatever is sitting on input 0, a 1 or a 0, it shows up on the COM pin, no matter what the other bits are. So I just wanted to make the distinction between analog MUXes and digital MUXes. Okay, so that's it for the normal class. Now we're going to do a homework problem. This is the Croft challenge, the Croft switch challenge. This is like the ice bucket challenge in TikTok. So when I was in school, there was a building that had a 4-story stairwell, and it had lights in the stairwell and light switches on every floor. And you could turn on and off all the lights in the stairwell from any one of these 4 switches. So your assignment is to figure out how that's done. And if you're an electrician, you already know how this works. Engineers, I'm not so sure about. By the way, the answer is back in Appendix 3 if you want to see it. I'm going to show you a hint here. This is how you do it if your building only had 2 floors. And I think we're probably all very familiar with this. You'd have your 120 volt here, your switches in this case, we're using 2 single pole double throw switches. When they're in this position, the light's on. If you flick either one of them, the light's going to go off. If the light's off and you flick it to either one of them, the light comes on. Well, I want to see how to do that with 4 switches. When I was in school, I asked my professor how to do this. And the professor sat down with some grad students and they started doing Carnot maps and they couldn't figure this out. So I never found that. This was back in the 70s when you couldn't go look it up on the internet. So
Are you still looking for the answer?
you know, no. About 5 years later, I was taking a class out in California on muxes, and they were doing all these switching circuits, and the answer came to me. So it only took me 5 years to answer this problem. So you guys should be able to do this in no time flat. So we'll talk about it next class, but everyone take a look at this, figure out how to do 4 switches. I think this is something every engineer should know how to do. Like I said, if you're an electrician, you already know how to do this. Okay, so in conclusion, analog IC schematics, they're very confusing. And the more you're exposed to common analog building blocks, the easier these schematics become to follow. Today I talked about current and voltage generators, switches and muxes. And these are very common building blocks used in many analog circuits. So I hope this talk has been helpful. And as always, I've included a glossary at the end of this document if there's any terms I used today that you want to go look up. So thank you very much for your time. There's a bunch of show and tell items on the table over here. Take a look on your way out. Thank you.